Hello students, welcome back to yet another session in this unit, that is electrical appliances. It is part of the second topic where we have completed other segments, and this is the third topic or third segment in second topic. We are going to complete in this session, that is electrical appliances. We are going to discuss here. So, as we discussed earlier, this is the content of Unit 5, and we are completing the second topic here. In next session, we are going to discuss internal heat load. It requires only one session, a simple topic we will be completing in 1 hour. And the for second topic is going to be completed in this session itself, and then we have apparatus selection, fresh air load, human comfort and IAQ principles, and remaining topics we will see in subsequent sessions. So heat gain from occupants, so appliances, occupant is also a appliance, and human beings contribute to cooling load in air conditioned spaces through and sensible heat due to body temperature and latent heat due to moisture in respiration and perspiration. So heat gain depends on the activity level of the person, and the number of people expected to be present in the conditioned space determines the total load, and number of people is also one of the factor. The heat gain is divided into sensible heat rises temperature and latent heat rises humidity level, and heat gain from occupants standard data in table. So that is next slide is based on 24 degrees Celsius dry bulb temperature. For 25 degrees Celsius temperature, room temperature, increase sensible heat by 10 percentage, so approximately 10 percentage, decrease latent heat accordingly, keeping the total heat constant. Adjusted total heat is based on female occupants 85% of adult male heat gain, and children occupants, so here 75% of adult male heat gain. So adult male heat gain is for males it is higher than female as well as children. For restaurants, sedentary work, you can see additional 17.5 watt per person included for food heat, and 8.75 watt sensible and 8.75 watt latent. And the bowling alleys, and 1 person per alley active, so that is 440 watts, and other seated 117 watt or standing 161 watt. So table, this is the table. You can see here degree of activity, typical application, heat, total heat adult male, and total heat adjusted, and sensible heat latent heat. And you can see here seated at rest. So very light work. So seated at rest is normally theater. It can be a matinee show, and very light work theaters evening show, and light office work offices, hotels and apartments, and moderate activity, it can be offices, departmental store and retail store, standing work drugstore, bank, sedentary work it is restaurant, light bench work it can be a factory, and moderate dancing it is a dancing hall, walking 4.8 kilometers per hour factory. Moderate heavy work, so bowling, bowling alley, and heavy work factory. So for this the total heat is given, sensible and latent heat is given like this. So when you see the total heat is very high in heavy work factory, that is 440, and this is one table for reference. Heat gain from occupants. Heat gain from occupants is dynamic and varies with gender, age, and physical activity. Indoor temperature, accurate estimate is critical for comfort cooling, dehumidification design, and tables help in standardizing HVAC load calculations. And there are many tables available, and we can make use of those tables. And heat gain from appliances. So appliances with air conditioned spaces can contribute significantly to internal heat gains. So these appliances may be electrical, gas fired, steam heated. Heat gain includes sensible heat raises room temperature, sensible latent heat increases moisture level in air. The data provided is for appliances without hoods, meaning that heat directly released into the room. So this is another table, heat gain from appliances without hoods in watts. So here the appliance is a coffee brewer, coffee warmer, coffee brewer with a tank 20 liters, coffee URN and coffee URN 13.5 liters and 22.5 liters, egg boiler and food warmer with plate, that is per meter square at top surface. So food warmer only per meter square top surface. So there are different appliances are given here, for which the electrical sensible and electrical latent, gas sensible and gas latent are given in this table for reference. So observations from this is appliances with larger water volumes or heating surfaces contribute more latent heat. So that is the more in moisture. And gas appliances often emit higher sensible heat compared to their electric counterparts. And hooded appliances are those ventilated externally will not add significant heat to the room. And key design considerations are account for both sensible and latent components in cooling load calculations. Consider appliances usage duration and frequency. Install vent hoods or exhaust fans wherever applicable to limit indoor heat gain. So heat gain from products. So its overview is like this. In cold storage, products emit heat due to chilling, freezing, cooling below freezing, respiration for some food items, and these loads must be considered to size refrigeration equipment appropriately. So heat gain from products, chilling load above freezing. So it depends on products mass and specific heat CPM and temperature drop T1 minus T2, chilling time TCH and QCH equal to MCPM into T1 minus T2 divided by TCH. And freezing load can be calculated like this. It depends on mass, latent heat of freezing HF, freezing time TF. So QF equal to MHF divided by TF. So here cooling load below freezing depends on mass, mean specific heat of frozen products C dash PM. So temperature drop T1 minus T2 and cooling time Tc. So Qc equal to Mc dash PM into T dash 1 minus T dash 2 divided by Tc. And product reaction or respiration heat. Some products, mainly fresh products, emit heat even in cold storage due to biological activity, and QR equal to M into evolution of heat per kg of food per hour. So this is another table, rate of heat production for different types of foods, and this is temperature degree Celsius, heat evolved per ton per 24 hours in terms of kilojoules. So apples and bananas, we have green and ripen and beets, cabbage, carrots, cauliflower. So for that different temperatures, and for that temperature heat evolved per ton is given here like this in terms of kilojoules. So the next is commodity cherries, cucumbers, grapefruit, lemons, melons, mushrooms, onions. We have other commodities like oranges, peaches, pears, peppers, peas, potatoes, raspberries. We have strawberries, tomatoes, ripened one, and turnips. So from this, the points to remember are the latent heat load arises due to dehydration or condensation of moisture from products. Moisture loss data is used to estimate additional latent load in cold storages. So heat gain from products include chilling, freezing, cooling, and respiration. So highly dependent on product type, mass, temperature, profile, and time, and critical in designing refrigeration systems for cold storage applications. So moisture losses for various products, it is important. It is having very good, very high importance, since moisture loss from products leads to latent heat load in cold storage. So there will be rise in moisture, and this contributes in increased refrigeration demand and product weight loss. So it depends on storage temperature, relative humidity, storage duration. We have nature of the product. So moisture loss for various products, and we have commodity, temperature, relative humidity, period for loss, moisture loss in terms of percentage, and we have commodities, the different commodities that we have seen earlier. So for that we have temperatures, relative humidity, period for loss. So this is 6 to 8 months for apples at a 0 degree temperature, and 2.8 degrees Celsius, it is relative humidity is 90, and 1 to 50 days. So period for loss. So moisture loss is given in the last column. So these are the different commodities, and for which how temperature, relative humidity, period for loss, moisture loss is happening. So from that table we can see higher temperature and lower RH increase moisture loss. And leafy and porous vegetables, so example cabbage, spinach, show higher loss percentages. And packaging and relative humidity control are essential for moisture retention. And engineering significance, if you see, use this data to estimate latent load in refrigeration systems, the system design, schedule rehumidification cycles in storage rooms, and design packaging solutions and insulation. Heat gain from lighting equipments. So next appliance is lighting equipment, and electric lights emit heat into the air conditioned space. Heat gain depends on wattage of lights, use factor, fraction of actual wattage used, and allowance factor is compensates for power loss, especially in fluorescent tubes. And the formula to calculate heat gain here is total wattage of lights into use factor into allowance factor. So use factor for residential and commercial, it is approximately equal to 1, and industrial it is lesser than zero point 0.5, and allowance factor for fluorescent lamps it is 1.25. So heat gain from power equipments. So here equipments like fans, motors, so convert electrical energy into heat. So normally fans and motors produces heat, and this heat is added to the cooling load if the equipment is located within the conditioned space. So the formula is, so QEM is equal to power rating of motor in terms of kilowatts divided by motor efficiency into load factor. So load factor is fraction of the total rated load at which the motor is operating. So if the fan is inside the air conditioned zone, the entire energy becomes sensible heat. So heat gain through ducts. So ducts carry the air conditioned air to different parts of the building, and it occurs when supply air duct passes through an unconditioned space. The duct gains heat from the surrounding environment, which adds to the cooling load. So also includes air leakage losses, and formula to calculate QD equal to UAD into TA minus TS, where QD is heat gain through duct, U is overall heat transfer coefficient, and AD is surface area of duct in meter square, and TA is ambient temperature, TS is supply air temperature in degree Celsius. So observations here, if ducts are entirely within the conditioned space, QD is normally 0. And if outside, so it must insulate to prevent condensation, temperature gain. So that the rule of thumb is duct gain is 5% of room sensible heat. So air leakage losses, it is the estimation only. The duct run time is long runs. So recommended leakage is 10%, medium runs 5%, short runs it is almost negligible. So the return air ducts experience similar leakage losses. For uncontrolled space, the air loss adds 5% to the load. So cooling load estimation for a conference room, a small example here. So problem statement is conference room for 100 persons to be maintained at inside conditions. Dry bulb temperature is 22 degrees Celsius. Relative humidity is 60%. Outside conditions are dry bulb temperature 40 degrees Celsius. Wet bulb temperature is 27 degrees Celsius. So other given data, sensible and latent heat per person is equal to 80 watt and 50 watt respectively, and lights and fans 15,000 watts, and sensible heat gain through envelope, that is glass wall and ceiling, is equal to 15,000 watts. So infiltration air is also present here, that is 20 meter cube per minute, and the fresh air supply is 100 meter cube per minute. Air mix equal to 2/3 of recirculated plus 1/3 of fresh air. So bypass factor of cooling coil is 0.1. So now objective is to determine so apparatus dew point, that is ADP, and grand total heat load. So ADP is apparatus dew point. This is also one of the important calculations in load calculations. Effective room sensible heat factor, ERSHF, effective room sensible heat factor. So these three we have to calculate. So first step, identify psychrometric points. So from psychrometric chart, point 1, outside air TA is equal to 40 degrees Celsius, TW equal to 27 degrees Celsius, that is equal to VS1, so equal to 0.911 meter cube per kg. So H1 enthalpy is 85 kilojoules per kg, and point 2 at room, inside room, TA equal to 22 degrees Celsius, relative humidity is 60%, and its enthalpy becomes 47.5 kilojoules per kg. And at point A, mixing point HA equal to 66 kilojoules per kg. So then infiltrated air also given, Mi equal to V1 divided by Vs1, that is equal to 20 divided by 0.911. So that becomes 21.95 kg per minute. And sensible heat due to infiltration, QSI equal to MIHA minus H2. So that is 21.95 into 66 minus 47.5. So that is equal to 6.77 kilowatts. And latent heat due to infiltration, QLI equal to MI into H1 minus HA. So that becomes 6.95 kilowatts. So next, internal heat loads. So persons are 80, 100. So 80 into 100 equal to 8 kilowatt latent. So that is equal to 50 into 100. That is equal to 5 kilowatt. And lights and fans, QL equal to 15,000 watt. So that is 15 kilowatt. So glass per walls per ceiling, that is equal to Qg equal to 15 kilowatts, and room total room heat loads. So sensible heat RSH equal to 6.77 plus 8 plus 15 plus 15, so that is 44.77 kilowatts. And room latent heat, that is RLH, so latent heat equal to 6.95 plus 5, that is equal to 11.95 kilowatt. Room sensible heat factor RSHF equal to RSH divided by RSH in plus RLH equal to 0.79. It is 0.79. So ADP can be calculated from psychrometric chart. Room air at point 2, so line 2 to 5 drawn from point 2 to parallel line RSHF equal to 0.79, and mixing point 3 lies on line 1 to 2 at TA3 equal to 28 degrees Celsius. Using bypass factor formula, TA4 minus TA6 divided by TA3 minus TA6, so that is equal to, so we have unknown TA4, that is equal to 13.15. So we know BPF is also given, so TA6 is equal to 11.5 degrees Celsius, so that is ADP, apparent dew point. So grand total heat load is equal to outside air total heat, that is OATH, equal to 0.02 into 20 into 85 minus 47.5, so that becomes 15 kilowatts. So grand total heat load equal to RSH plus RLH plus OATH, that is outside air total heat, equal to 71.72. By adding all these three, we get 71.72 kilowatts. So to summarize this, and we have to calculate the effective room sensible heat factor ERSHF. So from psychrometric chart, from line 6 to 2 is drawn to ERSHF scale, so that is 0.77. So the final answers to summarize here, the apparent dew point is 11.5, grand total heat load is 71.72, room sensible heat factor is equal to 0.79, effective room SHF is equal to 0.77. So these are the final answers, and we are completing this topic here, and we will be seeing the third topic from unit 5 in next session. Thank you, students. We stop here, and we will meet again in next session, and these are the books you can refer, and you can refer RS Kurmi book for this topic also. Thank you, students. We stop here. We will meet again in next session.